All right, so this video is going to be about forced harmonic oscillators. So in the last video, we came up with an equation that looked like mass times the second derivative of position plus a damping coefficient times the first derivative of position plus spring constant K times position was equal to, and in the last video we said this was equal to 0 because it was unforced. This section in the book basically just adds some kind of a forcing function over here. So as a reminder, this is what's going on. We've got some vertical spring that has some spring constant with a mass attached to the end of it, and it's in some kind of a, here I'll make it blue, like it's in water or something, I don't know. It's immersed in some kind of a fluid with a damping coefficient. And then what we're going to add on to that is that this mass is going to be pushed up or down with some forcing function, with some kind of an external force. So other than just explaining that, I'm not going to do another specific example with this, because what you really do is just exactly what we did in the last video. Find the mass, find the damping coefficient, find that K, put the forcing function on the right hand side, and then the only difference is that you have to use undetermined coefficients to solve it. So undetermined coefficients to solve. All right, so what I am going to do is look at some specific examples here. We're going to look at a specific example that is undamped. So we're going to take away that damping coefficient. And if you remember from the last homework in the last video, when you do that, when it's undamped, you get only cosine and sine in the solution. So I'm going to look at what happens when we have forcing functions that are also sinusoidal. So forcing functions that are also cosine or sine, because this is the most interesting example. So let's start with an example. Let's solve it, and then I'll talk about kind of what else we can do with that. All right. So I'm just going to give you the equation first. So let's solve u double prime plus 2u equal to 2 times the sine of t. All right, so as a reminder here, what we would get is that the mass would equal 1. We'd have some kind of a word problem where we'd get the mass is equal to 1, and the spring constant is 2, and we have that the forcing function is 2 times the sine of t. All right, so in solving this, remember that with undetermined coefficients, we first have to solve the homogeneous equation. So that's where we take out this right-hand side of it, we ignore that, and we solve it equal to 0, and we do that with the characteristic equation. So r squared plus 2 is equal to 0, so it looks like r squared is equal to negative 2, and that would make r plus or minus the square root of 2 times I. All right, so that makes the homogeneous solution. So I'm putting a sub h there for the homogeneous part. That makes that c1 cosine of root 2t plus c2 sine of root 2t. All right, now we have that particular part. Okay, so we need to make a guess here. Whoops, I just used y and we're using u's instead. I get so used to using y's. All right, so u sub p. So for our particular one, because there's a sign there, we need to guess both cosine, and there's just a 1. So cosine of t plus b sine of t. And this particular part does not match because the frequency or the period of the cosine and sine here is different from the period of the cosine or of the sine function on this right hand side. All right, now we need to plug this into this differential equation. So we need a first derivative, that is a u sub p prime, So derivative of cosine is negative sine, and derivative of sine is cosine. And then we need the second derivative. Derivative of sine is cosine, keep a negative out in front. And derivative of cosine is negative sine. Plug that into the differential equation. So the second derivative is negative, I'm going to put that over here so we have room, negative a cosine of t minus b sine of t, and then plus 2 times the initial guess, so 2a cosine of t plus 2b sine of t, and that is going to equal 2 times the sine of t. Then we're going to gather all our like terms. So I'm going to look at everything out in front of cosine, and I'm going to look at everything out in front of sine. If I look at this stuff out in front of cosine, I have a negative a and a 2a. So if I add those together, I've got an a on the left-hand side, and on the right, I've got no cosines, 0. On the left, I've got a negative b and a 2b, so add those together, we get b, and out in front of sine on the right-hand side is 2. Putting the entire solution together, I've got the homogeneous part, cosine of root 2t plus c2 sine of root 2t, and a is 0 and then b was 2, so plus 2 times the sine of t. And just a reminder that that is coincidental that this 2 is the same as this one. Alright, so there's our solution. Okay, so now what this means as far as this real world problem. So there's a couple things going on. So first of all, this root 2 right there, what that can tell us is that the motion without the forcing function, and so this is the natural period. So this mass, if it had nothing else forcing it, would naturally repeat every 2 pi over root 2. So just a little reminder here that the period of any sine or cosine function is 2 pi divided by the number that's out in front of t, and that is how often it repeats itself. All right, so this function right here, that naturally occurring motion without the forcing function, is going to repeat every 2 pi divided by 2. All right, on the other hand, we have this 1 right here, and so the period of the forcing function, so period of the forcing function is 2 pi divided by 1, so it's 2 pi. That repeats every 2 pi. So what happens here is that you have this mass that's bouncing up and down, just naturally repeating. Sometimes that forcing function is going to push the mass higher, and sometimes that forcing function is going to collide against it and slow it down. This is called beating, and I'm going to show you in the next slide how to graph this. All right, so this slide is about graphing beats. And just as a reminder from that last example, let's see, the important parts are r was plus or minus square root of 2i. So we got that the homogeneous part of the equation had like a cosine, I'll just write it all out, c1 cosine root 2t plus c2 sine of root 2t. So we need that part, and then the other piece that we need is from the natural period. And so I guess we can just go off of the forcing function. So the forcing function from that last example was 2 times the sine of t. All right, so to graph this, there's two pieces that we need. The first one is the frequency of the beats. And the frequency of the beats is really the question it answers is how often does the harmonic oscillator, which with its natural motion and the forcing function, so all of this combined, how often does that repeat itself? So how often does the motion of the harmonic oscillator repeat? Okay, so the answer to this question is that it repeats every square root of k over m minus omega, where omega is the number that's out in front of the t of the forcing function, all over 4 pi. All right, so in this example, so this, maybe I'll box that because that's one thing that we need, the frequency of the beats. So for this example, the frequency of the beats is square root of 2 minus 1 all over 4 pi. And so that, what I like to do with this is get a 1 on the top, and I'll tell you why in just a second. So let me show you what I do. Square root of 2 is about 1.4. I'm going to estimate here. So this is approximately over 4 pi. 1.4 minus 1 is 0.4. And then I'm going to divide by 0.4, so that gives me 1 over 10 pi. So what that does, I'm going to graph this whole thing up here. So this is going to be time and position, u, and I'm going to put a 10 pi over here. 10 pi, and then I'm going to make these envelopes, and so I'll do this in green because this is not actually the motion yet, but I'm going to make 2 different envelopes, and these are going to contain the graph of this motion. All right, but for right now, 10 pi, this is now where the motion is going to start to repeat. Okay, so that's one thing we need. The second thing that we need is the frequency of the rapid oscillations. So frequency of rapid oscillations. So oscillations, like a cosine or sine. So there are lots of cosines and sine functions within these 2 envelopes, and we want to know how many there are. And the answer, so this is how many sine or cosine functions there are within the 2 envelopes. Okay, so the answer to this is square root of k over m plus omega all over 4 pi. So in our example here, sorry, let me box this because we'll use that later. So in our example, this is going to be square root of 2 plus 1 all over 4 pi, and again I'm going to estimate this, and this time instead of getting a 1 on the top, I'm going to concentrate on the 10 pi. I want whatever is down in the bottom here to match with whatever I get from the frequency of beats. That was just important. I'm going to say that again. For the frequency of rapid oscillations, I want the bottom to match whatever I got from the frequency of beats. Okay, so square root of 2 is 1.4. I'm going to add 1, divide by 4 pi. So I get 2.4 divided by 4 pi. This is an approximation. And then I want to get a 10 pi. So again, I'm going to divide by 0.4 on both the top and the bottom. So if I do that, I get 6 on the top and I get 10 pi on the bottom. And what this tells me is that there are 6 either sine or cosine functions within the 10 pi. All right, so that means there's about 3 every envelope. So I'm going to start drawing these sine or cosine functions, but they need to stay within the envelope. Okay, so there's 1, there's 2, there's 3. Now, this can't repeat. I can't go up right now, otherwise it's going to look the same, and it doesn't repeat until the 10 pi. So it's going to do a little thing where it kind of starts to go down right here. And then there's 1, 2, 3. Now it's going to go up 1, 2, and it's going to repeat. So right in here is where it starts to repeat itself, the motion. And then let me kind of describe this. I'm going to trace it and describe what's happening. So what I'm saying here is that this harmonic oscillator is starting from rest. The forcing function goes with it at first, and it kind of gets higher and higher and higher, and then the forcing function is going to collide against it. And the harmonic oscillator is going to go closer and closer to 0, and then it's going to start going with it again, but in the opposite direction, and go higher and higher and higher, and then it's going to collide and go lower and lower and lower. And then it's going to start going with it again, but in the opposite direction, higher and higher. So you get the idea that the forcing function doesn't go along with the natural motion of the oscillator. Now, what's really interesting is something called resonance. And resonance is what happens when the period of the forcing function matches the natural period. And so what happens with resonance, I guess I'm putting it in red just because it's so cool. All right, so for resonance, and let me go back to kind of what we had there. All right, so our homogeneous, that looks horrible. Try again. Our homogeneous solution was C1 cosine of root 2t plus C2 sine of root 2t. So if our forcing function, if it was 2 times the sine of not just t, but if it was root 2t, then we would have resonance. And what happens is, graphically, you can start at 0 and this thing's going to oscillate, but what's going to happen is that the natural motion, the forcing function, is going to push that natural motion higher and higher and higher. And so really what ends up happening in real life is that stuff breaks. And stuff that breaks is like the Tacoma Narrows Bridge is an example of resonance, where the wind was sort of made, it was in, had the same motion as the natural motion of the bridge. Soldiers don't walk in cadence anymore over bridges, because in World War II there were a bridge that collapsed because the cadence of the soldiers matched the natural motion of that bridge, and it made it break. Earthquake design kind of takes all of this into consideration. So there's a lot of kind of interesting things that you can get out of this idea of resonance. All right, I think that's about it. Oh, I guess there's one more thing to mention, and that is just a side note here. You'll practice this, but here is the homogeneous. In order to get the particular part of the equation when you solve these, this automatically matches this function, and so you're going to have t's out in front. and taking those derivatives requires a lot of product rules. It just is a much longer process to solve these when they are in resonance. Okay, now I think that's all I got.